All right, let's jump right in. I want you to picture something for me. A single spruce tree, deep in a forest somewhere in the northeastern US. Looks pretty peaceful, right? But what if I told you that tree is the scene of a huge scientific mystery? A puzzle that, once you crack it, tells you a ton, not just about birds, but about how we do science in the first place. And this is the question that gets everything started. I mean, think about it. Any environment, right? It only has so much food, so much space, so much shelter. So how in the world can a bunch of really similar species all live in the exact same spot without one of them eventually pushing all the others out? It just seems impossible. So let's meet the stars of our show, 5 different species of warbler. And here's the thing, they're all so similar. I'm talking same size, they eat the same bugs, they all live and nest in the exact same kind of forest. It's a total head-scratcher, for sure.
And that, my friends, is what scientists started calling the Warbler puzzle. So back in 1958, this young ecologist, Robert MacArthur, he decides he's going to be the one to figure it out. He's watching these birds zipping around in the same trees, and he just knows something really interesting is happening here. Something that seems to fly in the face of everything we thought we knew about ecology.
Okay, so to really get why this was such a big deal, you need to know about this one rule in ecology. It's called competitive exclusion. And it's pretty simple, really. It just says that if you have 2 species going after the exact same stuff, the same food, same space, they can't live together forever. One is always going to be a little bit better at it, and eventually it'll kick the other one out. But here you have 5 species, all seemingly breaking that rule. It was a genuine mystery. So, how did he crack the case? Well, this wasn't something you could solve in a lab. No way. MacArthur had to become a full-on ecological detective. He goes out into these super dense forests with like binoculars and a stopwatch, and he just watches for hundreds and hundreds of hours. His original paper even talks about how tough it was to see anything in there, but he just kept at it, recording every single little move those birds made. And all that watching paid off. He started to see a pattern. This is basically the first big clue he uncovered, pulled right from his research paper. Turns out, the birds weren't just zipping around all willy-nilly. Nope. They had their own little highways in the trees. You had the Cape May warbler. It would move up and down. The black-throated preen. It would fly around the edges. And the Blackburnian? It would fly from the trunk out to the tips of the branches and back again. Totally different pattern. And that was the big aha moment. You see? They weren't really competing for the same space at all. It was like they were all living in the same giant house, but each one had its own private room. By moving and feeding in these really specific zones and patterns, they basically sliced up the tree into these little mini habitats. They'd created their own invisible traffic lanes in the air to stay out of each other's way. And you know, it was even bigger than just their flight paths. MacArthur realized it was a whole bunch of little things. They were eating in different parts of the tree, they had their own special ways of hunting for bugs, they even nested at slightly different times. Some liked the forest a little thicker, some a little thinner. It wasn't one thing. It was this whole complex, beautiful recipe for how to live together. So there we have it, a really elegant solution to a tricky puzzle, all figured out just by watching carefully. Science took a messy situation and found this hidden, beautiful order. So, case closed, right? We're all done? Well, not so fast. Because solving this puzzle was about to uncover an even bigger, more complicated one. And this is where the story takes a huge turn. Okay, so we figured out how these warblers do it. But is that a universal law of nature? Like, if we go to a totally different forest, are we going to find the same set of rules? And that right there, that is one of the biggest challenges for a science like ecology. The ecologist John Lawton really nailed the problem with this quote. And the magic word here is contingency. All that means is what happens in one spot depends entirely on its own unique history, its own specific circumstances. The rules change from place to place. The solution that worked for these warblers in one forest probably isn't the same solution for, say, finches on the Galapagos Islands. Just think about how different this is from a science like physics. A physicist, right? They can use the law of gravity to tell you exactly where a planet will be 100 years from now, anywhere in the universe. But an ecologist, they can't give you a simple law that predicts exactly which plants and animals you'll find in the next forest over. And why not? Because everything about that forest depends on its unique story. Was there a fire, a flood? Which seeds happened to blow in first? In ecology, contingency is absolutely king. So that leaves us with a pretty tough question, doesn't it? If every single ecosystem is just this one-of-a-kind result of its own history, is a science like ecology just telling stories? I mean, are we just collecting a bunch of neat anecdotes like our Warbler puzzle? Or is there a way to be more rigorous about it?
This is the core challenge of what people sometimes call the soft sciences. And that term isn't meant to be an insult, by the way. It's just a way of saying that fields like ecology or even psychology are dealing with systems that are just ridiculously complex. You've got history, you've got chance, all playing a huge role. And that makes finding those simple, neat, universal laws, well, pretty much impossible.
So that brings us back to the big one. If you're a scientist in one of these messy, complicated fields, and you don't have those universal laws to lean on, how do you actually make progress? How do you move beyond just telling interesting stories and start building real solid knowledge? Well, it turns out there's a really powerful tool designed for exactly this kind of problem. It was dreamed up way back in 1964 by a biophysicist named John R. Platt, and he called it strong inference. And it's basically a step-by-step method for cutting through all that complexity to find some clarity, even when you can't rely on simple law. So what's the secret sauce? Well, strong inference is all about a systematic process of elimination. Here's how you do it. First, you don't just come up with one favorite idea. No, you come up with a whole bunch of different possible explanations. Step 2, you design a crucial experiment. But here's the twist. The goal of the experiment is to disprove as many of your ideas as possible. Step 3, you do the experiment. And step 4, you look at which ideas survived and you start the whole process over again. Platt described it like climbing a tree. You're systematically checking every branch to see which one leads you higher. Now, you've got to realize this is a huge mental shift. The big idea here is that science moves forward, especially in these messy fields, not by proving that we're right, but by figuring out where we're wrong. Strong inference is just a really efficient way to find our mistakes and find them fast so we can get closer and closer to what's actually going on.
And Platt himself put it perfectly. He said, this approach forces you to focus on the problem, not on your favorite method or your favorite tool. It's so easy to fall in love with your own pet theory, right? But this process doesn't let you. Instead of just trying to prove your idea is the best, you're forced to look at all the other possibilities and systematically show why they're wrong. It keeps your eye on the prize, actually solving the puzzle.
Okay, so let's tie this all together. We started with a simple puzzle about some burns in a tree, and we found a really clever local answer. But that answer opened up a way bigger question. How do you even do science when every situation is unique? And that question led us to a really powerful way of thinking, strong inference, which teaches us that the fastest way to the truth is by systematically looking for where we're wrong. So this whole journey, from the top of a spruce tree all the way to the philosophy of science, it really leaves us with one huge takeaway. Real progress isn't about the ego trip of being right. It's about having the humility to find out where you're wrong and then learning from that. And honestly, that's not just a tool for scientists, that's a tool for everybody. So it makes you wonder, what's a pet theory you've been holding on to that you might be ready to really question?